so here's an example of with a pressure vessel with some torsion on it. This is for Class 15 in ME370, and the pressure vessel has an outside diameter 200 millimeters, a wall thickness of 8 millimeters, and has an internal pressure of 14 megapascals, 14,000 kilopascals. That's a lot. It's subjected to a torsion on the end of 25 kilonewton meters, and this material has a yield strength of 200 megapascals. We want to find the safety factors based on the maximum shear stress theory and the distortion energy theory, and we want to plot them on a failure loci. Boom. So here it is, the problem, and let's proceed through it. All right, so I get a little geometry out of the way here. Maybe the outside diameter is 200 millimeters, and the thickness is T, so the inside diameter is going to be the outside diameter minus 2 times the thickness, which we could actually probably do that in our head as 184 millimeters. Notice that the outside radius, easy enough, 100 millimeters, and we need that because we would like to check out and see what the thickness divided by that is going to be, and we get 8 divided by 100, and I think we could do this in our head, 0.08, which is less than 0.1, therefore thin-walled, right? Makes our life easier. It's going to have a torque, so I want J, I go pi over 32 times dO fourthed minus di fourthed. And you can do the math yourself and get 4.455 e to the minus 5 meters fourthed. So let's go for, these are geometry. We don't need to do anything with loads. They're all set for us. So let's go for the stresses. And so here's hoop P di over 2t. Right, it's on the outside surface, so we use this one. We don't use the one that's di plus t. That's only for the inside surface. And so that's what 14 times 184. Right, that's the reason why I got that one. I started to write the outside diameter. And thickness is 8. And I can just keep these in millimeters and that in megapascals because the millimeters cancel out. And so the answer comes out in megapascals. So we get 161.0 megapascals. And then for the longitudinal, that's 4t, right? So that's just 1/2 of this. So we could just 80.5 megapascals. And now for the torsional shear that's going to be on this thing, it's going to be TR over J. The torque was 25,000. R is to the outside surface, so it's the outside diameter divided by 2 to get to the radius to the outside. And then we have 4.455. That's supposed to be a 4, so is that. E to the minus 5. And we end up getting 56.12 megapascals. All right. So this is what the stress state looks like right here. We have tension, and we have see torque coming down. So if it's on this little H guy right here, it's going to be coming down that way off the face. So here are all the rest of the shears. So this is aligned with the x-axis right here. So he must be the longitudinal, 8.5 megapascals. And then this guy is the 161. And he is the 56.12 megapascals. And we'll get the Mohr circle for this. And that's going to be somewhere over something like this right there, right? So we're going to get a sigma A and a sigma B. And we're going to have a big Mohr circle right here. And there's the tau abs max. So we go through the whole process there of getting this, finding the center of this and finding the radius. And what we're going to find is sigma A is going to be 189.8 megapascals. Sigma B is going to be 51.74 megapascals, right? And then the tau abs max is really going to be 1/2 of this sigma A, right? So it goes sigma 1 minus sigma 3 divided by 2. Sigma 3 right here is 0, so it's just 1/2 of this right here. So we end up finding that it is 94.91 megapascals. I need to find my von Mises stress. And for the von Mises stress, I think the easiest one to use is the sigma A minus sigma A sigma B plus sigma B squared in the 1/2 right here, right? So shoving those things in there, I get the 189.8 squared minus 51.74. I should have put 189.8, but it doesn't matter. Flip-flop them. And we'll get 51, like a weird looking 51.74 squared, take the square root, and we will find, we get 169.9 megapascals. We had an alternative equation we could have used, just so you know. We could have said, instead, we could have gone back up to here, or onto here, I should say, and say that we have sigma x squared minus sigma x times sigma y plus sigma y squared plus 3 times tau xy squared. And if we plug all of those in there, right, with this being the tau right in there, we will get the same thing. So if we didn't need to find the maximum shear stress theory, we wouldn't necessarily need to do the Mohr circle and find the principal stresses. We could have gone to right here with our von Mises and saved ourselves some time. So anyway, the big thing we care about is the maximum shear stress theory is going to be the yield strength divided by 2 divided by the tau abs max. So the yield strength in this problem is 200 megapascals. So that's 200 divided by 2 divided by our 94.91. And so we get a maximum shear stress theory safety factor of 1.05. And then for our distortion energy theory, though, we're going to take our yield strength and divide it directly by the von Mises, because von Mises is really sort of converted into being a similar type of stress as the strength pull test. So 169.9, and so we get a distortion energy theory safety factor of 1.18. Once again, maximum shear stress theory is less than distortion energy theory, and that's generally the case. Sometimes they can be equal to each other if they're at the corners. That's gonna be true, but otherwise they're pretty much always going to be, the distortion energy theory is going to be a larger safety factor, and that means that this one's more conservative, it's more cautious. This one might be closer to what's actually taking place. So if we're going to plot these out, we will need, okay, so if you have to do a failure lookout, you have to do you have to get the principal stresses. So we have like 190 and call it 50, right? So 190 is going to be, right, so I think these are 120, 140, 160, 180, so 190 is like right there. And then 50, and he's going to be like right in there, right? So we're really looking at right about there. So my office hours are starting soon. And right there is where the failure is on the maximum shear stress theory, and right there is where the failure is for distortion energy theory, but right here is where we are. So I call that O, A, B, and C. And of course these are really, really, really small, so let's really zoom in. Let's see what we can do here. Let's use the smallest increment there with our millimeters. I could go crazy too if I don't have my digital calipers with me. I could get my digital calipers out. Ooh, that's going to jump around because it's so tight. But that looks to me like it's 32.5. B looks like he's a solid 31 to 34. It looks like a solid 35 to me. And then OC, it looks to me zoomed in like this is much easier to see actually zoomed in. And that looks like, okay, that would be 30 now. It looks like 38.5. So you can kind of see. So like if I'm going to go down to this down here and go to maximum shear stress theory approximately is going to be OB over OA, or what do you got here? 35 over 32.5. So that's 32.5 and divided, and we get 1.08. Right? Not too bad. 1.5. Okay. And we might get some sig figs, additional sig figs when we go to like compare them. So if I'm going to compare them, I'm going to say, and I'm going to say that this is the correct one. So I'm going to say that this is the approximation. So then I'm going to say, how do I want to do that? The easiest way is to go 1 minus this one divided by that, but that's fine. I'll do it the other way. 1.08 and 1.05 minus divided by 1.05, and we say that we are going to be 2.86% less than calculated. Right, so the graphical is 2.86% less than the calculated safety factor. The distortion energy theory is approximately, I'll make that approximately, OC divided by OA, and so that's going to be our 38.5 divided by 32.5, right? 38.5 and 32.5, and divide, and we get 1.18. Damn, 1.18, and so therefore virtually the same. I didn't keep what this exactly was, you know, with more sig figs, so they probably are off by a little bit. Well, this looks like it's, you know, for sig figs it's 1.185, right? So there might be some differences there. So continuing on with this, I thought this would be added value to put in a FEA. So I already kind of did this one. I did it in two different ways, right? So first off, I made a solid element thing, right? So this is all the dimensions, and I chose, they didn't tell us how long the thing was, so I just picked it to be like 500 millimeters. I just needed this to be sufficiently far away from here. I also made this end cap the same dimensions, so it just needs to be something there, otherwise we won't have longitudinal stress. And and I also put this little axis right in there. So I'll run another simulation to show what I did, as I just accepted my static loading. I made this thing. I just picked a steel. Like I could just pick my. Oh, by the way, this is in metric, but it doesn't really matter for the math of the thing. It will pick anything. I'll pick A36 this time. I'll see what happens. Anything different happens. And the only thing really the material takes into account is the elastic modulus and Poisson's ratio a little bit, but mostly elastic modulus. So the fixture right here is a fixed geometry I will fix this end right here. And for loads, I'm going to put a pressure onto the inside. And I'm going to do that surface and that surface. And I'm going to choose as megapascals. And it was 14, right? Sure. And now I need to put a torque on the end of it. I'm just going to cheat and put it on the end. One thing is going to happen is there's going to be a really high stresses right where these two things intersect with each other. But we only care about down by the length because we're just trying to get it to match. We're looking to try to match the thing. So here we want to use an axis right here. So I pick that face, but I also need to pick an axis. So I pick the axis. You can see the direction it's going, which is opposite from what we want. We want that direction. And here's our 25,000. Put them on there. And just as a first pass, let's just create a mesh. Boom. And there's our mesh. And it's not great. Look at through the thickness. You could consider that really only one element through the thickness. Sometimes you might consider that two elements through the thickness. I don't know. It's hard to say. But not great. But let's see what happens. All right, so we'll run the thing. Pretty fast results. I'm going to post-process it by changing the definition. It's already von Mises stress. I'm going to turn it into megapascals right there. Under chart options, I'm going to make it go from 0 to, I think 150, right? 150 might be, no, 150. Didn't accept 150 for some reason. It would jump back to something else. I don't understand why. I don't need to see the maximum because I know it's going to be like somewhere on here in the end. It looks like it's blowing up into be like a one of those blow up balloon balloon doggy things, whatever they call them, balloon animals. There you go. I'm going to change the output to be floating instead of scientific, and maybe I'll reduce it just to 1 decimal place, right? And I think by default I have it set as 10 increments. That'll work out well, I think, with my 150. Maybe we'll look, we'll see. And I like to have discrete, and might as well see what the mesh looks like in this case, right there. All right. So boom. That's pretty high. So I think maybe I might have used 200. I don't know. That looks like too much. I must have got like 200. Must have got 200 here. I think 200. I still, that's a lot larger than I had in the previous one. What did I use in the previous one? I want to see. I used 500. That's why. Okay. Yeah. Show. Yeah, but I guess it kind of makes sense. Actually, it makes a little more sense to have 200 in there because that's kind of in the range we expect. But anyway, I could take a probe and just put him right here on the outside. I get 165.5, and that's, remember, that's his von Mises, right? That's coming out here, and von Mises predicts that it's going to be 169.9. It's not bad, 165.5 compared to 169. And you could pick other spots on here too, and you can see that they're all pretty close to being the same. Here's 166. I got a 166 there. I'm just picking random spots there, but you can kind of see. But you also see that like it's like over here by the ends we have different things. We also see we have different on the inside as the outside, like slightly different, right? So we can even pick on the inside. Say what is it on the inside? 181, right? Because it's a higher stress on the inside than it is on the outside. Do the hoop, right? Do the hoop onto the thing. And okay, so now this was a confirmation, but also we might want to change the mesh, right? So where the heck are we? No, we want to go to mesh. There you go. And I'm going to create a mesh, and I'm just going to ramp that thing up to the finest that it'll do. Do I have other advanced settings? No. All right, so we mesh the thing, and but still through the thickness, there's still not a lot through the thickness. Oh, there's a weird guy right here. He made it across. That's weird. Kind of strange why he's different than the rest. I don't know. But we could run it and see if there's any change. See if there's any improvement. doing this kind of thing, as long as you're not like wasting time with like really crazy fine meshes, can be insightful, can be useful into trying to see what the what if kind of things. So we got 165.2. Didn't really improve all that much. 165. All right, so not great. But I have another thing that we can introduce, like something we haven't done yet. So I'll start fresh in this one, in a new part, and show you what we could do instead. Here is, an option. Solid elements aren't great for the thing that we are doing here because it's a thin wall. So instead, here I'll go on the right plane, and I changed to millimeters, and I'm going to make it just a circle with 200. And we could play around with this a little bit if we want to, but that's all we're going to do. And now I'm going to take that circle and I'm going to insert a surface feature, and I'm going to extrude it. Right? And you see that it'll extrude it into a surface. Not something that you've probably done very often. I'm only going to go 500 millimeters, and it even gives me the option to put an end cap on there, which is nice because that's what I want. So I have now made a surface, and you can see that it's open here on the back end here, but it looks like it's like a can. I made a can. And while I'm here, I'm going to make my axis down the center. Now let's go and make a SolidWorks simulation here and make for a new study. It'll be static. I'll define the part material. Once again, I'll go A36. Boom. I need to do something now though for the part. I need to go to Shell Manager. Right. So we have a Shell Manager. What I need to do is I need to tell it that what the thicknesses are. Right. So I think I can just click on both of these right here. These are just faces onto there. And I'm going to tell it that it's thin. I'm going to use the top surface. We could mess with that and see if that makes any difference, by the way. But I'm going to say this thing is the top surface. That means the thickness is going downwards, right? We didn't. The material, we're going to use that material right in there, yes. And the thickness is 8 millimeters. I think it's going to give me, it's going to turn all these things and go into this like little surface manager, and it tells me is redefined. Okay, so everything's defined. Say go yes, boom, right? And so that's just gotten ready for the mesh. I'll do my other things like my fixed geometry is just going to be that edge now. My external loads, I'm going to put pressure. Put them onto there and to there. And you notice they like to go from the outside, but that's still gonna, I need to reverse it, right? So yes, yeah, because it's an internal pressure, right? So that's the direction it should be going. And we'll change it to megapascals, and that's gonna be 14. And then I'm also gonna put the torque onto it. So we're gonna torque, we're gonna apply to this face, and we're gonna use about that axis. It's going to flip the thing around, and we know that it's 25,000. Did I do too many zeros? I think I did 1, 2, 3. There you go. Without the comma, I can't tell. Boom. And now mesh it. Create a mesh. Right. One thing that's important when doing if you're going to use surfaces, the gray and the orange, if you have multiple things that are attached to each other, you got to pay attention to the gray and the orange that they don't flip things around. The orange needs to match with the orange and that kind of thing. There's always going to be issues when you where the plates join, so you got to also be aware of that. But this is your introduction to plate elements. Because you have a surface in SolidWorks, you can use plate elements in SolidWorks simulation, and we can run it. And let's get all the same things out here for our results. So in our results, we will change it to megapascals. I will go from 0 to, what did I do down here? 200? Yeah, I did 0 to 200 this time. My previous time I did 0 to 500. And when I ran it before we were here together, like floating is, and we'll get down to only one decimal place, and we'll make it discrete, and we'll show the mesh. Boom. That's not going to be any different, but here's the probe. We take a look at the probe, we get 167.7, 167.3, 163.9. That's a little weird, that one. 168.7. So we're closer to a 169.9. We can possibly improve it. So let's create a mesh and make for more elements. By the way, see how fast it, compared to the meshing of the other ones, how fast it goes? That's one of the benefits of, and look how fast it's going to run. These are the benefits of running with the shell elements as opposed to the using the big fat solid elements. So if something is thin, these are the types of elements to run. And look how evenly distributed those things look like there. It's nice. Because this is very symmetric. We shouldn't see like a lot of jagged things going on here. So we take a little probe right here, 167.5, maybe a little bit of 168.9, maybe a little bit of improvement. I'd be interested, like I might run a side study. Like this is kind of some of the fun of doing FEA, of having this tool available, is you could start to experiment with things, right? So I might want to take a look at a couple planes right here. Let me create a plane and just drag him out there. I guess this guy right here. Boom, 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 boom. Let's go here and make a cut. Right. So I will go insert curve and a split line, and let's make a cut there by cutting this. Oh no, I got the wrong one. Projection, intersection. Projection, intersection. I think it's intersection, and I think let's see. This is splitting bodies, so that should be that guy, and this should be this right there. There's our preview. Good. So now we have a line, and that line has been cut in there. That means this is going to tell us that this is all messed up. So one of the things that's messed up is the pressure. So I'm going to edit that definition. Pressure 1 might duplicate it right here. Let's see. I want to edit this. Edit definition. Okay. Whatever. So it only could find that face. We're going to do that face and that face. Double check them. Okay. When we go to mesh the thing, create the mesh, you got to be careful. I might need to have changed this, the shell manager. Let's see. Let's go to shell manager. Does it recognize everybody? Okay, so we might need to go into here and recognize all of the parts. Do this again and make them all 8 millimeters. And I select the material. It's on the top, surface, thin. Let's see. It's going to give us. All right. So it gave me a duplicate of one of them. I think I have to be careful here. I don't know if I can see these. I think I just screwed something up because I have the thing on there twice. Let me see. I bet it's going to crash on me. Let me see. When I go to mesh is probably when it's going to create like the problems. Now you got to be careful. I might have that could have got screwed up. All right, so I might have to go backwards and fix something if I allow it to screw up too much. But I just wanted to look and do my post-processing using select entities and select this and update it, and you could see what the average is. The average is 167.6. We can also take a look at, here's like the little scatter of this. These could be interesting to see, because it's supposed to be one constant number all the way through, but it's not. So, but it's not too far off, right? You can see where the range. So some of them do jump up to the 169. So anyway, this is an FEA run onto this and confirming some. And now that we have distortion energy theory as one of our tools, we can do more stuff where we can make a comparison to what the computer gives us. It's easier to do. So there you go. That's a long 30-minute thing.